In this lecture, we will discuss turbulent external flows. It may be recalled that external flows or flows over objects that are immersed in an infinite stream. When we discussed laminar external flows, we saw that in the case of external flows, the drag force on object is generated due to two different mechanisms. One is, of course, the skin friction drag, and the second one, which is not present in internal flows but present in external flows, is pressure drag, which comes as a result of imbalance of pressure forces on the front and the rear side of the object. And in this connection, we defined bluff bodies to be those objects for which the contribution of the pressure drag to the overall drag force is much more than the contribution of skin friction drag. We start our discussion by looking at the flow over a flat plate, and the idea here is to develop expressions for the local skin friction coefficient as well as the boundary layer thickness as a function of x, that is distance from leading edge, or we can also write these relations in terms of the local Reynolds number or the x. So in the initial development, we assume the flow to be fully turbulent from the leading edge. This is not a limitation, because later on we will show how to modify this expression if part of the flow from the leading edge is laminar and then the flow transitions to become turbulent. So this is not a serious limitation as of now. So initially we look at flow over a flat plate with zero pressure gradient, for which the integral momentum equation that was derived earlier looks like this. Note that the integral momentum equation was derived without assuming the flow to be laminar at all or turbulent. So this applies in the general case. Now, when the external flow is turbulent, to begin with, we will say that the velocity profile in the boundary layer obeys the log law, which may be written like this. And we further assume that the log law profile is applicable until the edge of the boundary layer, which is not always the case. You must bear in mind that the turbulent boundary layer consists of three layers: the viscous sublayer, the overlap log law overlap region, and then the outer layer. So the log law region does not always extend up to the edge of the boundary layer, but we will assume that to be the case and apply it at the edge of the boundary layer. So we apply this at the edge of the boundary layer, set u equal to u infinity and y equal to delta, and we end up with an expression like this. By using the definition of the skin friction coefficient, which is nothing but tau wall divided by 1/2 rho u infinity square, we can relate the friction velocity to the skin friction coefficient. And if we substitute this into this expression, we get an expression that looks like this. Notice that in this expression, both CF and delta are the two quantities which we seek to determine as functions of x. So one more equation is required, and we can generate this equation by substituting the log law velocity profile into the integral momentum equation itself. So then this should actually result in an ordinary differential equation for the variation of the boundary layer thickness with x. And if the algebra is complicated, but if you go through the algebra, we now have two equations. One is this, the other one is obtained by substituting this into this. So if we go through the algebra, then we can actually get an expression for the skin friction coefficient, which looks like this. Notice that the skin friction coefficient is very high at or near the leading edge of the plate, and then decreases as a function of x. And the coefficient of drag, which is an integrated drag force over the length of the plate L, looks like this. So as the length of the plate increases, the coefficient of drag decreases because the wetted area increases. And this expression is called the Prandtl shifting formula and can be used for calculating skin friction drag in turbulent external flows. Now, we mentioned earlier that in the case of external flow, part of the drag is due to skin friction drag and part is due to pressure drag. Now, which means that in reality, we are going to encounter situations where there is friction drag in the presence of pressure gradient. Remember, this expression has been derived for zero pressure gradient. But in reality, we need to be able to calculate skin friction drag when the pressure gradient is non-zero. It is possible to modify these expressions or give corrections to these expressions to account for non-zero pressure gradient as well. So once that is done, we will then have expressions with which we can calculate skin friction drag over any object. Now, one of the shortcomings of the Prandtl shifting formula is that we started with the log law, and we already mentioned that the log law is not necessarily applicable until the edge of the boundary layer. But what is even more important is that the log law is not applicable all the way to the wall. In fact, it is applicable only up to the edge of the buffer layer, and it is not applicable all the way to the wall. Uh, which means that this can be a serious shortcoming. Now, on the other hand, the Spalding's equation, the law of the wall, is applicable all the way from the wall through the buffer layer to the outer edge of the overlap layer. And so, if we were to use the Spalding's equation instead of this equation in this development, we can expect the expressions for or the predictions for CF and CD to agree much better with experimental data. In fact, this turns out to be the case. White actually carried this exercise through, and the algebra is even more complicated than before. But he showed that it is possible to find much better agreement with experimental data for Reynolds number of 10 raised to 10 if we use Spalding's equation instead of the log law profile. And quite surprisingly, we actually obtained a very compact expression for CF, which looks like this. And this gives, as I said earlier, predictions which compare extremely well with experimental data for Reynolds number, local Reynolds number to 10 raised to 10. So in principle, there is no limitation on the use of this expression with Reynolds number. It can be used for any Reynolds number. Now, in contrast to laminar flow or a flat plate where roughness does not play a role, here in the case of turbulent flows, roughness does play a role. And we have already seen this in the context of turbulent internal flows. Okay, so the effect of roughness on the local skin friction coefficient has to be taken into account. So we saw that even in the case of internal flows, roughness affects the skin friction drag, and that is what we will try to take into account next. It may be recalled that in the case of internal flows, the roughness was characterized by epsilon over d. We can equivalently say that roughness was characterized by epsilon over r, where r is the radius of the pipe. So in case of passages which are non-circular, d may be interpreted as the hydraulic diameter and the r may be interpreted as the hydraulic radius, which is half of the hydraulic diameter. Now, after defining or characterizing the roughness this way, three regimes which were demarcated by the value of epsilon plus, which is defined like this, were also identified. So these three regimes were respectively the hydraulically smooth regime, for which epsilon plus was less than or equal to 5. The transition regime, for which epsilon plus lies between 5 and 70, 70, and the fully rough regime, for which the value of epsilon plus is greater than 70. Now, these observations can actually be carried over to external flows also, turbulent external flows also, with some minor modifications. For instance, the pipe radius R in the case of an external flow is replaced by the boundary layer thickness delta. And epsilon plus itself is defined in terms of the streamwise velocity component u star. Um, the streamwise velocity component in the case of a pipe flow was denoted W star, and in the case of boundary layer, the streamwise velocity component is denoted by U star. Okay. However, there are some important distinctions between the role of roughness or the character of roughness between internal and external flows. For instance, in the case of internal flows, roughness characterized by epsilon over R remains the same because both epsilon and R remain the same. They are constant. So the nature of roughness remains the same along the entire flow in the case of internal flows. Whereas in the case of an external flow, because we have replaced R with delta, and delta, as we know, increases with x. In other words, boundary layer grows with x. So epsilon over delta actually decreases as we move along the flat plate from the leading edge. So it is likely that the roughness changes character as we move along the length of the flow in the case of an external, turbulent external flow. That is one effect which was not seen in the case of internal flows. Now, in addition, it may also be noted that since U star is equal to U infinity times square root of CF over 2, and CF decreases with X, as we already mentioned, U star also decreases with X. So epsilon plus, which is defined in this manner, then also decreases with X. So CF decreases with X and U star consequently decreases with X. And now we see that epsilon plus also decreases with X, also although epsilon and nu remain constant. So consequently, it is quite likely that the roughness changes character as we move along the length of the plate from the leading edge. So since epsilon plus delta is small, and both epsilon over delta and epsilon plus are going to be quite high near the leading edge, it is quite likely that the flow may be in the fully rough regime near the leading edge of the flat plate, and then transition and then become hydraulically smooth as we move towards the trailing edge of the flat plate. This was something that was not seen in the case of internal flows. Now, Schlichting and Prandtl showed that in the case of external flow also, you could use the sand reference data that Mukherjee had generated for internal flows and apply the same kind of shift to the profile that was applied for internal flows. In other words, the entire profile is shifted down by delta B. So the B is placed by P plus delta B. And if we do that, then in the fully rough regime, we can actually obtain closed form expressions for skin friction as well as the coefficient of drag, which look like this. So it may be seen that just like in the case of internal flows, here also, in the fully rough regime, the skin friction coefficient depends only on the roughness and not on the Reynolds number. Because once we enter the fully rough regime, as mentioned earlier in the context of internal flows, the drag is due to form drag of the roughness, which now protrudes all the way into the buffer layer, and thus breaking up the sublayer. So it is due to form drag of the protuberances and not friction drag due to skin friction, which is why the coefficient of friction in this case depends only on the roughness and not on Reynolds number. Now, we mentioned at the beginning of this lecture that we assume the flow over the flat plate to be turbulent, fully turbulent from the leading edge onwards. Now, let us take a closer look at this. So here we are looking at experimental pictures of flow over a flat plate with zero pressure gradient. So this is a fluid here is air flowing at 3 meters per second past a flat plate. The initial portion of the boundary layer from the leading edge, which is not shown here, is laminar. And then it can be seen that transition begins to occur at this axial location. This is the top view of the plate and this is the front view of the plate. can be seen that turbulent spots begin to occur here, and the flow begins to transition as it is unstable, and the transition is complete by the time the flow reaches this location. Okay, so transition begins at 90 centimeters from the leading edge, where the local Reynolds number is 2 times 10 raised to 5, and then it becomes fully turbulent by the time we reach this axial location. Usually this distance is quite short, and we can assume the flow to be turbulent when we do calculations in this region. It does not make a significant difference to the final predictions. Right? So we can summarize this by saying that in the case of an actual flow over a flat plate, the flow is laminar up to a transition location, and then transitions becomes fully turbulent. And we account for this by doing the following. So the total drag force on the plate is equal to the turbulent drag force from the leading edge right up to the trailing edge of the plate, x equal to 0 to x equal to L, x equal to L. Then we subtract the turbulent drag from x equal to 0 to the transition location. Then add the drag due to the laminar flow from x equal to 0 to the transition location. Now, since the laminar drag is less than the turbulent drag, we can expect the overall drag to be less in this case than if the flow were turbulent from the leading edge onwards. Okay. So the total drag force then may be calculated as half rho u infinity squared times W, where W is the span-wise width of the plate, times turbulent drag over the entire length of the plate, minus turbulent drag up to the transition location, plus laminar drag due to up to the transition location. So the overall coefficient of drag in this case may thus be written like this. If I substitute this into the definition for CD, we end up with an expression for CD for flow over a flat plate with the transition occurring at x equal to x trans, like this. Normally, the transition occurs in the range of 3 times 10 raised to 5 to about 3 times 10 raised to 6. Although this transition Reynolds number may be hastened by tripping the boundary layer at some distance from the leading edge. As can be seen here, the flow has started transitioning at Reynolds number 2 times 10 raised to 5 itself, which could be the result of tripping of boundary layer or some rough spots on the flat plate itself. Any of these effects can actually trip the boundary layer into transition and becoming turbulent. But generally, as a guideline, we can say that transition occurs for Reynolds number between 3 times 10 raised to 5 and 3 times 10 raised to 6. So what we will do in the next lecture is to look at turbulent external flow over bluff bodies.